As reasoning models and agent workflows evolve, they keep tokens active longer. This constant retention pushes standard transformer architectures past their hardware stress limits. The new baseline for a highly capable AI agent requires holding up to 1 million tokens in active memory. Under standard attention mechanics, computation scales quadratically. Every new token added to a sequence must be checked against every previous token, causing required memory and compute power to multiply aggressively as the sequence lengthens. This diagram shows a standard GPT-style decoder block. The primary structural culprit for this memory explosion is the key-value cache. The attention layer stores the key and value tensors for every passed token. Approaching 1 million tokens, that storage requirement creates an exponential spike in memory traffic. To bypass these hardware constraints, open-weight developers are dismantling and specializing the homogeneous GPT block. The survival of local AI workflows depends on mutating the architecture's fundamental mechanics to cheat the laws of memory scaling. Google's Gemma 4 suite illustrates a direct approach to optimizing inference for mobile and edge hardware. This diagram shows 2 adjacent transformer blocks in Gemma 4. In a standard setup, each layer computes its own query, key, and value projections. Gemma drops the key and value calculations in layer n+1. Instead, it recycles the key and value tensors from layer n. It calculates a new query to form its own attention pattern, but reuses the heavy data from the layer above. By sharing roughly half the key and value tensors across its 35 layers, the smallest Gemma model halves its KV cache size, saving 2.7 gigabytes of memory at a 128,000 token context window. Dropping those layer-specific operations creates a deficit in the model's overall representational capacity. Gemma recovers that capacity through per-layer embeddings, a parameter-efficient method to inject token-specific information without scaling up the heavy transformer stack. Notice how the per-layer embedding slice bypasses the expensive main attention block entirely. It prepares a small token-specific vector outside the main loop and adds it directly into the residual stream at the end of the block. Poolside's Laguna XS.2 uses a different method of capacity restriction, called layer-wise budging. It restricts the compute-heavy global attention layers to 6 query heads, while allocating 8 query heads to the cheaper, local sliding window layers. Dropping or recycling internal operations defends against sequence scaling by exchanging total model capacity for the ability to run locally. Rather than skip operations entirely, architectures like Xia 1.8b attempt to compress the data itself. On the left side of this diagram, we see the baseline multi-head latent attention used in DeepSeek V4. It compresses key and value vectors for storage in a latent node. However, to perform the attention dot product, it must expand them back out to their high-dimensional state. Now look at the right side. Xia introduces compressed convolutional attention. The query, key, and value streams compress, but the matrix multiplication happens directly inside the narrow latent space, outputting a single compressed vector before expanding. This dual mechanism shrinks the storage cache and directly reduces the computational flops required during generation. The mathematical vulnerability here is expressivity. Executing attention in a compressed state strips away the local context the model needs to weigh token relationships accurately. To inject that missing context, Xia applies a 1D sequence mixing convolution to the compressed query and key vectors immediately before the dot product. By forcing the heaviest matrix calculations to occur inside a compressed bottleneck, developers break the quadratic scaling law governing standard attention. DeepSeek V4 operates under a more aggressive constraint, processing a full 1 million token context window at a fractional cost. This timeline represents a sequence of tokens. Where other models compress the width of the individual token representation, DeepSeek V4 compresses the length of the sequence itself. It uses 2 distinct mechanisms. Compressed sparse attention applies a sparse top K selection to pick only the most relevant blocks from the sequence, ignoring the rest of the history. Heavily compressed attention takes a denser route, physically crushing large groups of up to 128 tokens into a single unified entry. Because the HCA cache is now drastically shorter, the model can execute a highly accurate, dense attention pass over those heavily compressed entries without spiking memory. DeepSeek V4 interleaves these 2 layer types, balancing the targeted detail retention of sparse selection with the macro-level efficiency of dense compression. Achieving million-token memory requires sacrificing absolute token-level fidelity, substituting precise history with highly synthesized macro summaries. Shrinking the attention mechanism addresses memory, but deep models face a secondary computational bottleneck, the central residual stream. A single residual stream limits the volume of information that can flow through ultra-deep networks layer by layer. This diagram maps a structural change called manifold-constrained hyperconnections. It splits the single residual highway into 4 parallel streams. A distinct mapping matrix shuffles information laterally across these 4 streams. This routing occurs outside the attention and feed-forward layers, moving data without forcing it through compute-heavy parameters. Deep parallel routing introduces severe mathematical risks. Without strict limits, stacked mapping matrices will cause signals to either explode toward infinity or cancel out to zero. DeepSeek secures this routing with a doubly stochastic constraint. Every entry in the routing matrix is forced to be non-negative, and every row and column must sum exactly to 1. This guarantees stable redistribution. Parallelizing the residual stream allows models to drastically increase their internal reasoning capacity without paying the compute tax of widening the attention layer. This schematic unites 4 structural mutations. Top, Gemma and Laguna skip operations and reallocate budgets. Bottom left, Zaya forces math into a compressed latent space. Bottom right, DeepSeek V4 splits the residual highway and crushes the sequence dimension to sustain massive context limits. These divergent strategies render raw parameter counts obsolete as a comparative metric. True capability is dictated by a model's effective size and how intelligently it routes memory. Training data determines the ceiling for reasoning quality, but architecture determines if a model can run in the real world. Conquering the frontier of agentic, million-token AI requires a ruthless, structural deconstruction of the very mechanisms that built it.